So let's get into discussing homework from section 1.5. We introduce a kind of an interesting thing here. We introduce the, if we have a, let's let A be an M by N matrix. In linear algebra, anytime you start getting flustered when you're talking, just start by saying, let A be an M by N matrix. And that gets things going. We've talked about the equation AX equals B. We want to talk about the associated homogeneous equation. I'm going to say it the other way. We've talked about the homogeneous equation, but we want to talk about the homogeneous equation. So this could be associated with an equation AX equals B. So just to make sure that we're all on the same page, the homogeneous part is equaling 0. Notice that A is still an M by N matrix. X is going to be a vector in Rn, because X has to be N by 1 for this multiplication to even work. And the vector over here is a 0, and it's a 0 vector. And that is the 0 vector in Rm. This is the 0 vector in Rm. So the homogeneous equation AX equals 0. So one thing we want to notice about this equation is that this equation is always consistent. The homogeneous equation is always consistent. The reason that the homogeneous equation AX equals 0 is always consistent is that the augmented matrix A0 could not have a pivot in its rightmost column. The augmented matrix cannot have a pivot in its rightmost column. So all we have in the rightmost column of this augmented matrix are a bunch of zeros. They will always just be zeros. The rightmost column of the augmented matrix for a homogeneous matrix equation will always be, will never have a pivot in its rightmost column, so the homogeneous equation is always consistent. If we look at an equation AX equals B, what we're getting is going to be a shift. So graphically, what we're getting, or geometrically, what we're getting is going to be a shift of the solution to the homogeneous equation. So with this in mind, let's think about any question, or let's talk about any questions that you might have on the exercises and problems from section 1.5. Any questions? 1.5, go ahead and type them in the chat. 16 and 18, let's start with those. So in 16, perfect, that's what we just talked about. We want to describe and compare the solution sets of x1, oops, let's write those down. 1.5, 16. We want to compare x1 minus 2x2 plus 3x3 equals 0, and x1 minus 2x2 plus 3x3 equals 4. So if I look at the, sure I'm on camera, if I look at the reduced row echelon, the augmented matrix for each of these systems or equations, they're like very small systems, we're looking at 1, -2, 3, and then 0. That's the only row in the augmented matrix. If I write down the general solution, I'll see there's a pivot in the first column. So x1 is a basic variable. And I'll write it in terms of the free variables, x2 and x3. So x1 is going to be 2x2 minus 3x3. x2 and x3 are free. If I look at this solution set in parametric vector form, we're going to get a plane in R3 because we got 3 entries. So in parametric vector form, we've got, let's see, x2. x1 is 2x2, x2 is 1x2, and x3 has nothing to do with x2. Then the x3 column will be x1, which is -3x3. x3 has nothing to do with x2, and x3 is 1x3. So there's the solution set in parametric vector form. So the solution set to the homogeneous equation is the plane spanned by these 2 vectors. So the solution set is a plane spanned by these 2 vectors. The span of those vectors is a plane. Everybody see it? I went very quickly through that. I went from linear system to augmented matrix. The reducer echelon form of the augmented matrix nothing changed. I wrote down the general solution, including explicitly stating my free variables. I converted my general solution to parametric vector form, and then I was picturing in my mind what the solution set looks like. Moreover, we notice that the solution set contains the origin because there's no constant. So the solution set is a plane spanned by these 2 vectors, and it contains the origin. Now let's look at the other equation, x1 minus 2x2 plus 3x3, the same relationship between x1, x2, and x3, but now we want it to equal 4. So the augmented matrix will look like 1, -2, 3, and then 4. We still have only a pivot here in the first column, but now our solution set, our general solution, has x1 equal 4 plus 2x2 minus 3x3. And x2 and x3 are still free. But the difference is, instead of going through containing the origin and just being the span of these 2 vectors, I've got this constant. Instead of looking at the equation y equals mx, I've now got y equals mx plus b, and b is not 0. So my solution set here in parametric vector form will have 4, 0, 0. It'll start off with a constant plus x2 times 2, 1, 0 plus x3 times -3, 0, 1. So I've got the solution set for the non-homogeneous equation is a plane because it has 2 vectors that have weights on them, and then 1 fixed vector. So this solution set is parallel to the solution set to the homogeneous case and shifted through the point 4, 0, 0. This is a shifted version of the homogeneous case. Oops. So say it's a shifted plane parallel to the plane from the homogeneous case. So that's geometrically what we want to think about in 1.5. We want to think about the homogeneous case being the span of a set of, the homogeneous solution set is the span of a set of vectors. And then if the non-homogeneous case, we'll just take that same plane and shift it. So we want to compare that, we want to think about this equation as being y equals 0 plus mx, and this is b plus mx. Because that's all we're doing, is solving linear equations. Any questions on 16? Cool. We have an 18 that might be different. So problem 18 and problem 6, notice that we have the same coefficient matrix. So yeah, we have the same coefficient matrix in 6 and 18. So we're just going to get a shift of the solution set from problem 6. Looking at this, the coefficient matrix from problem 6, we can see that there's going to be, well, I'm not sure what the reduced echelon form looks like, but I think there's going to be a free variable in x3. Looks like there's a free variable. Looks like x3 is a free variable. If x3 is a free variable, then the solution set is going to be a line. So let's find out. Let's take a look at 18. Now I'm going to do the reducer echelon form of just the one from 18. So I'm going to do 1, 2, -3, 5. Because by doing this one, I'm also doing the homogeneous case as well. Just ignore that last column. And then 2, 1, -3, 13. And then -1, 1, 0, -8. All right, so here's a reduced echelon form of the augmented matrix from problem 18. And if I just replace the 7 and the -1 with zeros, it's also the reduced echelon form of the augmented matrix from problem 6. So since there's one free variable, there's going to be the solution set will look like a line. So let's actually write this down. So 1, 5, 6, and 18. Our equation, our augmented matrix by rows was 1, 2, -3, 5, and then second row 2, 1, -3, 13, and third row -1, 1, 0, -8. And the reduced echelon form of this augmented matrix was 1, 0, 0, 0, 1, 0, -1, -1, 0, and then 7, -1, 0. So we have pivots in the first row, first column, and a pivot in the second row, second column, and then no more pivots. If I think about the variables, x1, x2, and x3, we can see that x3 is a free variable. So the solution set, x1 will equal 7 plus 1 x3. x2 is a basic variable. I spelled 2 wrong. Where we have -1 plus x3, and x3 is free. So in the parametric vector form, I've got a constant, 7, -1, 0, plus our multiple of x3, which is going to be 1, 1, and 1. So this third row, the third entry is going to be 0 plus 1 x3, because that's what x3 free means, 0 plus 1 x3. So we can see that the solution set is going to be a line in the direction of 1, 1, 1, containing the point 7, -1, 0. That's what this solution set looks like. So the solution set is a line, because there's only one vector for the free variable. There's a one-dimensional solution set. The solution set is a line in the direction of 1, 1, 1, containing the point 7, -1, 0. We can read this as B plus M times X. If we look at the solution set in 1.5.6, instead of 7, -1, 0, we get 0. We just get 1, 1, 1 times X3. Any questions? Is everybody okay? All right, so what do we got in 22? In 22, line M through P and Q. So line M goes through P and Q. So you want the direction from P to Q. Just subtract those two vectors. If you look at Q minus P will be the direction that we're looking for. And it contains one of those points. So in 22, the line M, oh, they even tell you, M is parallel to the vector Q minus P. So the equation of the line should be P plus X times Q minus P. So here's the equation of the line. Oops. P is where it starts, and Q minus P is the direction. This is just a variation on the equation. Let's say y equals b plus m times x, where we start at b and add m a bunch of times. Any questions? In 26, if A is a 3 by 3 zero matrix, then if we multiply the zero matrix by anything in R3, we'll definitely get 0. So the solution set to AX equals 0 is all of R3, because 0 times everything will equal 0. In 20, so we want through A parallel to B. So we just want A plus B times X. Start at A. And then go in this direction. So 3, -2 plus -7, 6 times X is what it would look like as vectors. 3, -2 plus X times -7, 6. Oh, I'm not trying to write secret things. I needed to scroll. How's everybody, okay? There was so much to remember, and now I'm like, oh, hey, geometry stuff. And you're like, oh no, there's so much to remember. That's only because it's a lot to remember. And I'm asking you to remember all of it. All right, let's pause the video here and start thinking about linear independence.